We're continuing to look at limits as we go off to positive and negative infinity, and looking at limits that go to positive or a negative infinity as we approach some x value. So in front of us is an example, and I said last class period I'd come in and I needed to do a couple more examples like this and give you a kind of a trick of how to handle these. If we look at this example in front of us, which says the limit as x approaches infinity of the rational function x minus 3 all over the square root of 4x squared plus 25. If we go in and we do direct substitution, we get that indeterminate form of infinity over infinity. And so that doesn't tell us anything. And this is where we went back and we manipulated it. The trick was to look at the degree of the denominator, and then we were going to multiply by a fancy 1 over x to that highest power. Notice that in the denominator, we have that radical. We cannot break that down as the square root of 4x squared plus the square root of 25, but we can think about that as what degree would that be? And so the highest degree, if I think about taking the square root of x squared, that's just x. So the highest degree of the denominator we can think as a power of 1. So we want to manipulate this, and we want to multiply this by 1 over x, both to the top and to the bottom. The problem is that I can't distribute this 1 over x underneath the radical. So I'm going to manipulate this so that I can multiply it underneath the radical. So I'm going back to algebra. There's a rule that if we have the square root of a times the square root of b, we can rewrite this as the square root of a times b. There was a couple of little minor stipulation there that a and b cannot both be negative. If they're both negative, then we can't do that. But we're going off to positive infinity, so we're okay there. And so let's just think about this. 1 over x, I want to rewrite this so it has a radical. And so this is the same thing, right, as 1 over the square root of x squared. Let's even go a step further. We can use that rule because I know the square root of 1 is 1. So let's just rewrite this as the square root of 1 over x squared. And this is true for x greater than 0. So when I'm multiplying this, instead of putting 1 over x in the denominator, let's write that 1 over x as the square root of 1 over x squared. I'm going to bring down my limit. As x approaches infinity, if I distribute 1 over x times x in the numerator, I just get 1 minus, and if I distribute 1 over x to this 3, I get 3 over x. All over. So I'm using this rule. Both of them are the same index, square root, that I can distribute this underneath the radical. So basically I have that square root of parentheses 4x squared plus 25. I want to write this out. All times that square root of 1 over x squared. So I'm going to distribute that underneath the radical. Oops, I'm sorry. And I don't have the square root there anymore because I put it underneath the radical. So let's now distribute it. So my numerator is staying the same, so I'm just going to rewrite that. The limit as x goes to infinity of 1 minus 3 over x all over. So now when I distribute this, 1 over x squared times 4 over x squared underneath that radical, that would just give me 4. Plus distributing the 1 over x squared to the 25 and under the radical in the denominator, I get 25 over x squared. And so now as we look at the limit as x is approaching infinity, we plug in infinity wherever we see an x. Notice there's pieces in here that are going to 0. So a number over infinity goes to 0. So we have this 3 over x as x goes to infinity goes to 0. And this 25 over x squared as x goes to infinity also goes to 0. And so we're left with in our numerator 1 all over square root of 4, which we can reduce down to 2. So this is equal to 1/2. So if you went to go graph this function, y equals x minus 3 all over the square root of 4x squared plus 25, you should see that as x goes off to infinity, you have a horizontal asymptote at 1/2. So the graph is getting closer and closer to 1/2, hugging that line as it goes off to infinity. We need to be careful though, if we're looking at x going to negative infinity. So let's look at one example with that. Before I pull up that other example, let me see if there's any questions. So looking at the same example, except now we want to look at what's happening as x goes off to negative infinity. And so again, if we do direct substitution, in this case, I see I get negative infinity in the numerator. All over, well, negative infinity squared, that's a positive infinity, times some 4, that's still positive infinity. Adding 25 to that, that's still positive infinity, and taking the square root of infinity is still infinity. So here, this is the same thing. I can think of this as -1 all times infinity over infinity, if you like. And so this again is an indeterminate form. And so again, we're going to multiply by that fancy 1. And we're going to manipulate it so that we can bring it down into the denominator. And put it underneath the radical. So again, that highest power in the denominator, we can treat it like it's an x. So we can multiply the numerator by 1 over x. The denominator, though, is 1 over x. I got to be a little bit careful because x is going to negative infinity. And so if I was multiplying this, this would be going to negative infinity, this 1 over x. And so I have to be careful. I need to write this as, how about the square root of 1 over x squared, but there's a negative in front. Because x is less than 0. So if you guys are okay with that, then we're going to write this as negative square root of 1 over x squared. If you're not okay with that, maybe just thinking about a real life example. So choose any value of x less than 0. So let's just choose an easier one. So maybe x equals -2. If I plug this back in here, -2 for 1 over x, I get -1 over 2. Or 1 over -2. If I plug in -2 for x in here, this gives me back this negative square root of 1 all over. I'm plugging in -2 and squaring it. -2 quantity squared. So this is negative square root of 1 all over -2 quantity squared is 4, and the square root of 1/4 is 1/2. And so I wouldn't have gotten -1/2 if I hadn't put that negative out in front of that radical right here. Okay, so now I'm going to distribute. I can distribute underneath that radical in the denominator because we're multiplying a square root times a square root. I'm going to keep this negative out front when I do that though. So the limit as x is approaching negative infinity, distributing 1 over x to this x gives me 1, minus distributing 1 over x to the 3 gives me 3 over x. And this is all over, I have this negative outside my radical, and then distributing this 1 over x squared to each term in my, underneath my radical, my radicand. So 1 over x squared times 4x squared. X squareds cancel, and I'm just left with a 4, plus 25 times 1 over x squared is 25 over x squared. So now when we go in and we plug in negative infinity wherever we see an x, a number over negative infinity that approaches 0. So I have 1 minus that approaches 0. So 1 minus 0 all over the negative of the square root of 4 plus, well, 25 over x squared as x goes to negative infinity, that also goes to 0. And so we're left here with 1 all over the negative of the square root of 4. And this is equal to negative 1/2. Okay, so I see that this graph, if I graph this, has a horizontal asymptote at 1/2 and negative 1/2, depending on if we're going to positive or negative infinity. So I'm going to pause the video as I pull up the graph so we can just look at the graph of it and just show what we just found is correct. Okay, so in front of you, we just graphed our function that we were looking at as the limit was going off to positive and negative infinity. And if you look at this, as we go off to positive infinity, notice that line, the graph is hugging the horizontal line of 1/2. That's 0.5 here. As we go off to negative infinity though, and we found this algebraically, we're heading towards negative 1/2. And that's what we found algebraically by looking at the end behaviors by taking the limits as x goes to positive and negative infinity. Okay, so we've just spent a lot of time looking at the end behaviors of graphs of rational functions by looking at the limit as x goes to infinity and negative infinity. Now we're going to go back and look at these vertical asymptotes, which we kind of talked about a little bit the first day we spent on this section. So in front of us, we're going to find the limits of the following. The first one is the limit as x is approaching 0 on the right of 5 all over 2x. I notice in here that x cannot be 0 because that would set my denominator equal to 0, right? If I did direct substitution in here, I would get this is equal to 5 all over 2 times 0. This is equal to 5 all over 0, which is undefined. So I actually know the limit doesn't exist, but I want to know what's going on with the graph. I also know that there's a vertical asymptote at x equals 0. So let's see, is that shooting off to positive infinity or negative infinity? Well, if we're approaching 0 on the right-hand side, that means that when we choose values to plug in for x, we're choosing values that are positive. So x has to be greater than 0. And so if we think about this, we have 5 all over 2 times some positive number that's really small. How to write that? Okay. Well, if that happens, this piece, and this is a positive number, 5 all over 2 times some positive number that's really small, is actually going to blow up. And this is going to go to positive infinity. If I looked at this as a limit as x approaches 0 on the right, sorry, I just did the right, the left, This time when I'm plugging in values for x, x is less than 0. They're very small, getting closer and closer to 0, but on the left-hand side. And so when I'm plugging in numbers that are negative, 5 over 2 times a negative number, well, 2 times a negative is negative. And so this one is going to be going off to negative infinity. So we have a vertical asymptote at x equals 0, the y-axis. And as we're approaching 0 on the right, this is shooting upwards, approaching positive infinity. And as we're approaching 0 on the left, it's shooting downwards. We can go a little further, and if we wanted to look at the limit as x is approaching infinity, well, the limit as x is approaching infinity, positive infinity of 5 over 2 times x. This is 5 over infinity. A number over infinity goes to 0. And so I notice that I have a horizontal asymptote here. This is approaching 0. Same idea as I'm going to negative infinity of 5 over 2 times x. Well, this is 5 all over 2 times negative infinity is negative infinity. And that also goes to 0. So let's look at another one. This next example, we're looking at the limit as x approaches negative 5, and it's from the left-hand side of our numerator, which is 3x, all over our denominator, which is 2x plus 10. So technically, really, we would be going in and doing direct substitution. But again, I notice if I do direct substitution, I'm getting 0 in the denominator, right? If I went in and plugged in negative 5 wherever I saw an x, I get 3 times negative 5 is negative 15 for my numerator, all over 2 times negative 5, which is negative 10 plus that 10. So negative 15 over 0, which is undefined. But we want to see what's going on. Are we shooting off to positive infinity or negative infinity? So if I'm coming in on the left-hand side of negative 5, the numbers that I'm plugging in are less than negative 5. Let's think about that. If I plug in a number less than negative 5, let's think about our numerator. Is it going to be positive or negative? Well, 3 times a number less than negative 5, that's going to be a negative number. All over 2 times negative, or number less than negative 5. 2 times that number less than negative 5, and then adding 10 is also going to be a negative number. It's actually not the same number though. And so a negative over a negative, that makes it a positive number. And so that tells me that this has to be shooting off to positive infinity. Where if I looked at what's going on as I'm coming in on the right-hand side of negative 5, Well, those are numbers that are bigger than 5, -5. So if I plug that into my numerator, well, 3 times a number close to -5, it's still negative. 3 times a negative number is negative. All over, so something less than -5, but close. That's going to give me a number less than 10. So a number less than 10 plus 10 gives me a positive number. So I can tell that as a limit as x is approaching -5 on the right-hand side, this is negative infinity. So if I was to graph this, at -5, I have a vertical asymptote. We can denote that by a dotted line. It's really not on the graph, but it just shows us that it's vertical and we're approaching that, but never crossing it. So as we're approaching -5 on the left, we said that it was shooting upwards. This was coming upwards. As we were approaching it on the right-hand side, we said that it was shooting downwards. Well, let's see about horizontal asymptotes. Horizontal asymptote, we would get infinity over infinity, or negative infinity over negative infinity. And so we have an indeterminate form. Look at the degree of the denominator, which is 1. So we're going to multiply by that fancy 1 over x in this case, all over 1 over x. So if we distribute that to our numerator, we get 3x times 1 over x is just 3, all over 2x times 1 over x is just 2, plus 10 times 1 over x is 10 over x. And so as that goes to infinity, 10 over x goes to 0, and we get back 3/2.
Miss Knopfsinger, really quick, are we going to look at some trig examples too?
Yeah, we can look at some trig examples too. Definitely. Right. Thanks for reminding me.
Yeah.
So this is going to go to 3/2. So I actually know I have a horizontal asymptote right here. I know it's going to be crossing the x-axis somewhere. I could easily figure out what that is by setting my equation equal to 0. So let's just find the x-intercept. Let y equals 0. So we got 0 is equal to 3x all over 2x plus 10. Clear the fraction, we get 0 equals 3x. X is 0. Just curious of where that was crossing. Get a little more accurate. Okay, so we got something that looks like this. Let's just look at and make sure that our horizontal asymptote is the same as we go off to negative infinity. So let's look at the limit as x goes to negative infinity of this 3x all over 2x plus 10. Again, we get negative infinity over negative infinity, indeterminate form, multiply by that 1 over x, both to the numerator denominator. And so we're going to get the same thing. We're going to get 3 all over 2 plus 10 over x. And so again, we're going to 3/2. So a little off over here. So as we're going to negative infinity, we're going to 3/2. And as we're approaching -5 on the left, we're going to positive infinity. So we were able to find the end behaviors of the graph, which they have horizontal asymptote and the vertical asymptote, and what's happening on each side of our vertical asymptote by looking at limits. Okay, so there was a question about looking at trigonometric functions. Let's look at that really quickly. Or not so quickly. Let me first see if there's any questions on this before I start. So let's say we wanted to find the limit of x approaching infinity of cosine of x. Well, if you think back of the graph of cosine of x, you got a wave function at the origin, or not the origin, x equals 0, we have 1, pi halves, we have 0, pi, we get -1. And it just continues and it's periodic. So it just is a wave function that bounces back and forth between our y values of -1 and 1. So as this is going off to infinity, there's no one particular y value that it's going to. And so the limit as x approaches infinity of cosine of x, this does not exist. Same thing with sine of x. But now let's look at this. Let's say instead we wanted to look at the limit as x approaches infinity of cosine of x all over x. Well, I know my cosine of x, that's bouncing between -1 and 1, back and forth, back and forth. And then my x value down below, that is shooting off to positive infinity. So as cosine of x is going to infinity and x is divided by x going to infinity, what's happening is our wave is actually getting smaller and smaller. It's getting closer and closer to this x-axis, and it's still same period. And so this is actually going to be tending to go towards 0. Same sort of idea if I look at the limit as x approaches infinity of sine of x over x. Sine of x over x, the range is between -1 and 1. And then I'm dividing by something that is getting really, really huge, and 1 over a huge number goes to 0. -1 over a huge number also goes to 0. So this goes to 0. Same reasoning about plus or minus infinity. So this
is the computer lagging? Are you writing?
Of course I am.
Sorry, I didn't see. I'm sorry. I'm losing.
No,
I'm like, is it
no,
lagging?
no. Darn it.
I was just about to ask.
Okay.
Yes,
hold on.
that's
I was getting scared. I'm sorry. I panicked.
No. It's good that you tell me right away. Let me see. See if I can stop. I shut everything down before I started, so I didn't have all these things open, hoping that would go. Got rid of all my downloads of my files. Let's see. Okay. Okay, so I was just mentioning that it doesn't matter as this goes off to positive or negative infinity, cosine of x over x or sine of x over x, we're still going to get back 0 because again, cosine of x and sine of x, their y values between -1 and 1, dividing by something going to negative infinity. 1 over something going to negative infinity, or -1 over going over something of negative infinity is going to 0. So let's use that fact to look at a couple of other trigonometric limits. So let's look at the limit. How about of theta going to infinity of theta plus sine of theta all over 2 theta plus 7 minus 5 times sine of theta. Okay, so if I put in infinity, wherever I see an infinity, I see that I get infinity plus or minus 1 or a number in between. So that's infinity. All over 2 times infinity plus 7, which is infinity, minus 5 times some number between -1 and 1 is also infinity. So we got this indeterminate form, and we wanted to go back and manipulate it. Same kind of idea that we had done before. So let's look at the degree of the denominator. So 2 theta, that's a degree of 1. So let's multiply both the numerator and denominator by 1 over theta. And let's distribute it to each piece in the numerator and in the denominator. So if we do that, we get the limit as theta goes to infinity. Well, theta times 1 over theta is 1, plus sine theta times 1 over theta, well, sine theta over theta, all over 2 theta times 1 over theta is just 2, plus 7 times 1 over theta is 7 over theta, minus 5 sine theta times 1 over theta is 5 sine theta over theta. And so now as we look at theta going to infinity, that sine theta over theta, that goes to 0. 7 over theta as theta goes to infinity goes to 0. And this 5 sine theta over theta as theta goes to infinity also goes to 0. And so this would be equal to 1 over 2 or a half. So it's pretty much the same as what we were doing before. And so don't get caught up that there's a sine theta or cosine theta in there. Just knowing that it bounces between -1 and 1. And then if we divide that by a theta, that piece has to go to 0 as theta goes to infinity or negative infinity.
I have a question. Doesn't you said I remember sine like something sine of theta over theta, wouldn't that be 1?
You are correct if we were looking at the limit as x approaches 0 or theta goes to 0. So you're talking about if we have the limit as x approaches 0 of sine x over x, this is equal to 1. But if we're going to infinity or negative infinity, that's equal to 0.
Okay, thank you.
Mm-hmm. So in front of us is that graph of sine x over x. And so we can see as the limit is approaching 0 on the left and the right, our y value is 1. And it was shown by the sandwich theorem. But if we look at the limit as x is approaching infinity and negative infinity, notice that line is getting closer and closer to our x-axis 0. And little teeny waves going back and forth. And so the limit as x goes to negative infinity and infinity of sine of x over x is 0. So we've seen that 0 over 0. We talked about that being indeterminate. Infinity over infinity, that's indeterminate. But we can't have infinity minus some infinity. That's also an indeterminate form. So let's look at an example where we might get this infinity minus infinity and how to manipulate that to give us what we want, an undeterminate form. And so if we look at the limit, let's say as x approaches infinity of the following parentheses, so the square root of x plus 9 underneath the radical minus the square root of x plus 4 underneath the radical. And so if we plug in infinity wherever we see an x, we get this infinity minus infinity. This is in an indeterminate form, and we got to go back and manipulate it. Okay, and so the way to manipulate this, again, is to multiply by a fancy one. Imagine that. And this fancy one that we're going to use is going to be the conjugate of what we have. So the conjugate of what we have, remember the conjugate changes the sign in between our radicals. So I want to multiply this by the square root of x plus 9, change the sign in between, plus the square root of x plus 4, all over our denominator, the square root of x plus 9, plus the square root of x plus 4. So recall, we just did this so that we have a difference of squares. So let's rewrite this. So now I have the limit as x is approaching infinity. So difference of squares. So I can just square the first term, the square root of x plus 9. If I square that first term, I get x plus 9 minus the square of the second term. So the square of the square root of x plus 4, that's just x plus 4. I need parentheses around that whole piece though, x plus 4. All over the denominator, square root of x plus 9 plus the square root of x plus 4. And so if I simplify, I distribute this negative inside that parentheses. I get the limit as x is approaching infinity. I have really an x minus an x, which cancels. And I have in top a 9 minus 4, which gives me 5. All over the square root of x plus 9 plus the square root of x plus 4. So now when we go do direct substitution and we plug in infinity wherever we see an x, we get this 5 all over infinity plus infinity, which is infinity. And 5 over infinity, this goes to 0. Okay, so you have some examples in the homework that you're going to have to manipulate because you get this infinity minus infinity. And all you're going to do is multiply by that fancy one, and that fancy one is just going to be the conjugate of what you were originally given. Okay, so this example, we're given information, and with that information, we want to graph something that where all this information we're given, it holds true. So we're given f of 0 is 0. So to me, that tells me I have a point when x is 0, y is 0. So I have a point here. It tells me that the limit as x goes to infinity and negative infinity is 0. So that tells me I have a horizontal asymptote on my x-axis. It tells me that the limit as x approaches 0 on the right-hand side is 2. So on the right-hand side, I have an open circle here, but I'm approaching it. Getting closer and closer as I come into 0 on the right. I know I'm going to be hugging the x-axis, so I could come down like this. And then the last piece that I'm given is that the limit as x is approaching negative 0. I'm sorry, 0 from the left is negative 2. So I know I have an open circle here at 0, negative 2. And I'm coming in, and on the left-hand side, I'm getting closer and closer to that value, but never reaching it. And then I also know I have a horizontal asymptote at y equals 0 as x goes to negative infinity. So here is one example of what the function could look like with all of these conditions held. And so there's an infinite number of solutions that you could have graphed, but this is just one case that holds.